Good afternoon to all. So we have discussed so many things in design of brake system aspect. So as you see, all these topics in red mark are covered. In fact, we have discussed the brake distribution, the brake force distribution. Also, we have discussed about the optimization. In fact, we will understand more optimization aspect of the for a brake force distribution by solving problem. Today we will focus, today maybe another couple of lectures we will focus on problems. There you will understand many things. Yeah, this is the problem number 6. It's a big problem. The Tata Venture GX model van has a length, width, height, dimensions are 3950, 1565, 1878 in millimeter. The rated maximum gross weight GVW of the van is 19.52 kilonewton. The wheelbase is 2540 millimeter and the ground clearance is 160 millimeter. The height of the CG, nothing but center of gravity, is 650 millimeter above the ground and 1000 millimeter in front of the rear axle. Okay. The wheel size 650 millimeter dia, 150 millimeter wide. The coefficient of rolling friction is 0.02. The aerodynamic drag coefficient is 0.3 and the coefficient of road addition is 0.85. Determine A. What should be the braking proportion in the front and rear axle to get optimum braking effect? That is a question number 1. Then also find the same braking proportion, not same means solving the braking proportion for I surface where mu s equal to 0.1 if the vehicle travel on the same surface. B. If the van with the above braking proportion traveling at 70 km per hour on a level road, having the coefficient of road addition is 0.7 and the coefficient of rolling friction is 0.015 is braked. In that case, which wheel will skid first? What is the maximum deceleration rate achievable? This is the question. Okay, maybe I should give some more clarity. If the van braking, above braking, that is what is clearly given, right? It is above braking means its meaning about the above talking about concrete surface, not the ice one. Okay, it is talking about the concrete surface. You could see what are the data do we need. We need to know about the weight of the vehicle. This is your wheelbase, okay, and this is your H height, right? Center of gravity from the ground level. And what does it mean? This one, what is it? 100 mm in front of the rear axle and the center of gravity. It's a L1 or L2? It should be L2. Excellent, correct. This is L2. And this is your mu r, this is your mu r, and this is your mu s, 0.85. All those informations given. So we need to find out what would be the optimum braking effort. That's the thing. Okay. So data were given. I'll reiterate again. Data were given. W 19.52 kilonewton. Yeah, that's clearly given. And the wheelbase L is given 2540 millimeter. Okay. From the problem, L2 given 1 millimeter, sorry 1 meter, okay, or 1000 millimeter. Obviously, L1 will be 1.54 meter. Yeah, that's clearly given. Okay. Then the mu r equal to 0.02 and H is given 0.6 meter And what else is missing? We are okay. Radius given, right? The diameter of the tire is given, right? Yeah. Diameter of the wheel is given as a 0.65 meter. Okay, that is given. Yeah. The case 1, right? A, we want to take concrete surface. When you say concrete surface, the typical is 0.8 to 0.9, but specifically is given in the problem. Your road addition factor is 0.85, right? So we have to find out what is the optimum your KB front axle divided by KB rear axle. This is what we need to know that. Okay. So if you want to write the equation, the front axle, KB rear axle, okay, L2 H mu S and mu R divided by L1 minus H mu S plus mu R. Okay. So can you substitute the values please in this equation? One 0.65 clearly given, 0.85 plus 0.02 divided by, this should be 1.54 minus of 0.65 . Okay, that's give me 1.566, 0.9745, which comes as a 1.606. Yeah, 1.6606. This is nothing but your KB front axle and KB rear axle. The ratio only. This is the ratio 1.606. But already we know that your KB front axle and KB rear axle, alright, the summation always should be 1. So if you using these two and substitute, finally you would expect the KB front axle, okay, front axle 0.62 or else we can write a 62. A KB rear axle, right, so 0.38 is nothing but your 38. So this is a proportion, yeah, this is your proportion of distribution proportion at the front axle as well as the rear axle. Okay, that is fine, that's a fine. So now given this condition, we know this, the surface is concrete, which is road addition factor 0.85. Already we have we got the distribution, the brake distribution force for front axle as well as the rear axle also we got it. Can we find out what happened if this road addition and this is the distribution, how does the which will log first, we will find out. Then we can go for the next one. What is the next one? They are asking about using the same braking proportion if mu s is changed, right. Ultimately what we want to understand, how if you have a same road addition, if you change the brake distribution, what is going to be happen, or else if you have this same distribution but changing the road addition factor. Both way we are trying to understand that. Okay, that will give us the role of critical role of the distribution as well as the road addition factor or coefficient of road addition mu s also. Okay, this is we got it now. Okay, this is with the proportion aspect. Okay, we will do it for eyes later. Now we need to identify which will log first, right. We need to identify which will log first. So your A by G, the front axle, okay, mu s, remember this equation L2 KB front axle into mu r KB front axle, okay, minus of mu s h by L. If you substitute, tell me what is the value you are getting. 0.85, 2.54 plus 0.62 is a KB front axle, right? Yeah. Right. It should be 0.86. This is the value you should expect. Your A by G, the front axle 0.86. So already we got the one value, right? A by G rear axle now. The deceleration rate. This is nothing but your deceleration rate. Yeah. Mu s L1 by L. This 1 minus KB front axle, okay, into mu r 1 minus KB front axle plus mu s h by L. Substitute the value, please. This 1 minus KB FA nothing but your KB rear axle, which is 0.38, and mu r equal to 0.02. 0.38 plus 0.85 into 0.65 divided by 2.54. So now the A by G RA is coming as a 0.87. Okay, let me ask question. So already we know the A by G, right? The front axle came 0.86. Tell me which will lock first. Are they almost same value or different values? Right? Can we consider they are almost same? Yes or no? Yes, we can consider. So for one particular road addition 0.85, we got the optimum KBF, KB and front axle and KB rear axle, and try to find out which will lock first. So we got the deceleration rate. Deceleration rate looks are equal. So they will lock at the same time. Both axles will lock same time. Both axles lock at the same time. Okay. Now look at the problem. Now saying that using the same proportion, we are changing the surface mu s equal to 0.7 and mu r equal to 0.015, I think. Okay. So in that case, what happened to your the deceleration rate? In that case, do you expect the same behavior or same phenomena, or would change? That's what we are going to understand in the problem statement. Okay. Yeah. For keeping the same braking proportion, we will try to find it which will lock first. For given mu s equal to 0.7 and mu r equal to What is the mu r equal to? It's a 0.015, yeah, right. So substitute please, A by G front axle. I'll straight away put the values rather than the rewriting the formulae. 0.7 and 2.54 plus 0.62. So that should give me 0.646 for okay, 0.646, maybe I will make it a 65. This is my front axle, yeah. Similarly for the rear axle, this is 0.38, 0.015. That's give me 0.77. So tell me what is happening from this value, right? Your your front axle deceleration rate, front axle is lesser than the rear axle, right? That's what happening. So in this condition, which will lock first? Front axle will lock first, yeah. Now let me ask question. So what do you understand now? We are using the same proportions. We are using the same proportion. If you change your mu s, obviously the scenario completely changed. Remember when we derived the equation, we said this is valid at one particular road addition factor. If the road addition factor or value change, obviously the scenario locking of the wheel will change accordingly. Okay. So there is one more scenario. Will keep the road addition same, but will change the proportions. That a later stage I will give you a problem, right. So obviously the front axle or the wheels at the front side will skid first. This is what happening here, yeah. So fine. So the one more question is clearly given, okay. The one more question clear. Find out if road addition factor 0.1 for ice surface, what would be the brake proportions, right? Yeah. For ice surface, mu s equal to 0.1, right. Can you find out please KB front axle? Just substitute the values. 1 plus 0.65, this should be 0.1 and 0.02, 1.54 minus of 0.65, expect 0.737. This is your KB front axle and KB rear axle. The proportions, I am sure we know that again the summation of both proportion should come as 100, right. So if you solve these two things, A and this is the B, so finally we would expect your KB front axle equal to 42, the KB rear axle equal to 58. Look. So earlier what was the value we got when you have a concrete surface mu s, when you 0.85, there your distribution of the KB front axle was 62, right, rear axle was 38. Now the moment you change the surface condition, what happened to your the road addition, the moment you change the road addition value, the distribution also will change. So when the distribution change, what do you expect the deceleration rate? Do you think the both the front and rear will have same deceleration rate or different deceleration rate? Will be different. So again, so that's how we have to find out somewhere how to optimize it. Okay, let me ask one more question. See, ultimately in this problem given GVW, gross vehicle weight, right? What happened? This is the vehicle is fully loaded, and if you have the vehicle without any load, that means only the vehicle weight and one passenger, which is the driver. What do you expect? That is also will alter, right? So we need to make attention in this aspect also. So we will discuss in subsequent lectures in this the brake distribution optimization aspect, and we can go for one more problem. So now we will do another problem. Okay, please note down this another problem. Problem number 7. A passenger car weighs 20 kilonewton as a wheelbase of 2794 millimeter. The center of gravity is 1270 millimeter behind the front axle and 508 millimeter above the ground level. In practice, the vehicle encounters a variety of surfaces with the coefficient of road addition ranging from 0.2 to 0.08 and the coefficient of rolling resistance of 0.015. With the view of avoiding the loss of directional stability on surfaces with the low coefficient of addition under emergency braking condition, what would you recommend regarding the braking effort distribution between the front and rear axles? Okay, so this is what a problem. Yes, this is similar to the previous problem, but there is a slight change, right? There is a slight change is given. So we have the vehicle weight, which is 20 kilonewton. You can see that, and the wheelbase is given 2794 millimeter, and this is actually that is the wheelbase, and this is the center of gravity is 1270 millimeter behind the front axle. What do you mean by behind the front axle? L1, it's not L2. Okay, remember this is your wheel, right, and this is the center of gravity. It says behind means something backward in this direction. So obviously that means L1. Yeah, that means L1, which clearly given as a L1 is given 1270 millimeter, and this is your H. That's from the above ground level. Clear? This H is given, and you have to change the mu s by from a 0.2 to 0.8 with the mu r is clearly given as a 0.015. Okay, with the view of avoiding the loss of directional stability on surfaces with the low coefficient of addition under emergency braking condition, what would you recommend regarding the braking effort distribution between the front and rear axle? That is the question. So what do you understand that? Yeah. So what do you understand? What do you mean by loss of directional, avoid loss of directional stability? There are two things. When the front wheel locks, what will happen? The what is that? There is a directional instability is different. Directional instability one is there, and loss of direction one is there, right. So they are both different. Loss of direction means you can't steer or move the vehicle either to the right side or the left side, that is loss of direction. Okay, that will happen when you have a front wheel lock first. Front wheel lock first, that will happen. Okay, if the rear wheel lock first, what happen? Because of that you will have yaw effect, so you will have a spin. So that is the direction, loss of directional stability. Both are different. Stability, directional stability different, loss of direction is different. Okay, so they are asking, they are expecting you want to avoid rear wheel lock first. That means you want to aim to lock front wheel. That's how you have to design. Okay, so that's a problem. Yeah. So W is clearly given 20 Newton, 20 kilonewton, not 20 Newton, 20 kilonewton. Okay, L is 2.794 meter, L1 is 1.27 meter, L2 obviously L equal L1 plus L2. So from this you will find out L2 equal 1.52. Yeah, meter is clearly given. Okay, H is given. H is given 0.508 meter, and mu r is 0.015. So what we have to do, mu s ranging from 0.2 to 0.8. That's what the problem. So we will take away straight away two things, the lower limit and upper limit, and try to find out what is happening. Okay. So first, this is lower and this is a low L, and this is upper limit U. Okay, for mu s equal to 0.2. I am not writing equation anymore, just substitute the values and give the answer straight away. So this is the KB front axle and the rear axle. So if you substitute individually, what we get, I am giving answer straight away. FA equal to 58, the KB RA 42. So this is the value you are getting. So this is for a mu s equal to 0.2. Okay, mu s equal to 0.2. Similarly, for mu s equal to 0.85. So we had to find out the values also. Can you give me the values please? What is that value you are getting? Yeah. I am sorry, yeah, 0.8 radii, yeah, correct. Is 1.52, right? 0.8 plus 0.015, 1.27. Yeah. So finally the value is coming as a 2.259. Separately write the KB front axle, rear axle 6931. Okay, this is for when you have a mu s equal to 0.8. So individually we got the proportions, right? So front axle and rear axle proportion we already got it. So what is the next step is we need to find out the deceleration rate for both surfaces. Yeah, we need to find out the deceleration rate for both surfaces for mu s equal to 0.2. That's what we are going to do now. A by G front axle 0.2, 0.52, 2.79 plus 0.58, 508, right? Yeah, to 0.015. I think 1 minute. There's a mistake. This is distribution, right? The distribution mu s is what we are getting for I surface. I'm sorry. Yeah, 0.58. Okay, 0.58, and this should be also 0.58. Yeah, there was mistake. Then 0.08 by 2.79. Expect 2.216, right? This is A by G front axle 0.216 when you have mu s equal to 0.02. Then similarly for the rear axle, substitute the values again. When you do that, this should be 0.42 a kb, right? The entire board went to the very slant. So what is the value you are getting here? Supposed to be 0.42, right? Yeah. So I think 0.28. I'm getting this one. Yeah. So there is a huge difference. Okay, there is a huge difference here. So from here, what do you expect? This is the front axle, and this is A by G, rear axle. So the front axle has a 0.216, right? 0.216, which is lesser than the your rear axle. So what happened in this condition when the mu s equal to 0.2? So rear will lock first or front will lock first? Right? Front will lock first. Yeah. Lock or skid first. So similarly, already we know the ratio also. We found the ratio for a point mu s equal to 0.8 as a 69:31, right? Already we have. What is the value for mu s equal to 0.8? Right? I think we just now did 69:31, right? Yeah, 69:31. So now we'll go for the A by G. So what is the value you are getting? I am straight away giving the value. So what is the value you are getting now? Front axle, yes. So you should expect, I am straight away giving the answer 0.027 and 0.8094. So we got, so again A by G the front axle, A by G rear axle, okay. Your front axle lesser than the rear axle, right? So here also the front will lock first, okay. The question is, you have chosen the two different surfaces, one is mu s equal to 0.2, the other one is 0.8. In the both cases, what is that you are getting, right? Both will is the front will lock first. So any recommendation do you want to give? Because it's clearly mentioned loss of directional stability. So it is satisfied, right? Nothing to need to be give any recommendation. So this proportion is fine, okay. I think I'll stop now. I think this I think we have done the two problems to understand about. In next class we are going to discuss various aspects. If today we discuss mu s, if you have having one mu s at different proportions or having one proportion and different mu s, how is going to be, where is the way to you draw the optimum proportion, how will you achieve it, those things we will discuss in next class. And also not only that, see the braking, so far we never discussed about braking distance, right? How to achieve the braking distance, that is also we are going to discuss, okay. And one more critical thing, so far we discussed when you apply through brake pedal, the force is goes there and activated through either in the disc brake or drum brake activation force, you are having a torque, that is one side. The other side, the vehicle is moving, certain velocity, you are applying a brake, again the distribution coming from your wheel and road surface, that is another torque we are there. But how to connect them, where is that connection, that connection also we are going to discuss in forthcoming lectures, okay. Thank you.